Hello, everybody, and welcome to the Latin American Webinars of Physics. Today, we are very happy because we are in the webinar number 114 of this series of the Latin American Webinar of Physics that we started in 2015. So today we are going to have a very interesting talk by Professor Michele Doro. Michele Doro, he's an associate professor in the University of Padova. And before that, he done a postdoc in the Instituto Astrofísica de las Altas Energías in Barcelona, in the Autonomous University of Barcelona. And the talk that he will give to us is, the title is Trinity, a compact air shower detector for ultra high energy skimming tau neutrinos. So welcome, Michele, and we are very happy to have you here in this law physics cycle. For all the people, just a little before, for all the people that are following us in the live YouTube streaming, you can ask questions to Michele in the chat, so you can find it very easily. And Michele, welcome to law physics.
Thank you, Roberto. Thank you, everybody, for joining this meeting of today. And I want to thank Roberto for the invitation first and congratulate with you because, as you said, this is number 114. And I remember when I first read, I learned the word webinar with you and with this effort that you did many years ago. And I was surprised back then how, to make speeches in remote, but then it became reality. So you have been a precursor of this kind of circulation of science. So really, congratulations for keeping this for so long. Okay, thank you for the introduction. Shall I start with the presentation of the?
Yes, please.
Okay.
You can share your screen. And...
yeah, sure. Okay, so let me share my screen. Should be coming. No. Okay, here. Great. Can you see it?
Yes, perfectly.
Okay, great. So this presentation that I'm going to do today is about a novel design of a telescope to detect neutrinos, okay, in the ultra energy range. And this presentation was, I basically presented it a few weeks ago at a conference in Venice. So this presentation is on behalf of the Trinity collaboration. You can have more information here. There is a small web page, and I reported here if I can share the slides after all with you with the basic papers describing this new design of telescope. I want to underline that I work for the Dipartimento di Fisica and Astronomia here in Italy, in Padova. It's where I'm talking now. I'm also a member of the INFN, that is the National Institute of Nuclear Physics. You're welcome to come to Padova. It's a beautiful town, and next year we will be celebrating 800 years of our university. Okay, so let me make a spoiler already of what I will be talking to you in the next minutes, because it will more or less shape what I want to say. So we want to propose a telescope system composed of 18 similar telescopes. There will be so-called air shower imaging Cherenkov telescopes. Okay, it's a technique. I will briefly introduce it, like CTA, MAGIC, Veritas, HESS, but it will be used to detect tau neutrinos. Okay, and the technique is called Earth-skimming because the basic idea is depicted in the picture. So you have the Earth profile here. You have a neutrino, and especially a tau neutrino. And the skimming is that you basically skim the surface of the Earth. So there is a direction in which the neutrino crosses a certain path in the ground, within the ground, and there is a probability that it emerges as tau, converts to tau, and emerges And if you have a tau, a charged particle in the atmosphere, is where you have a shower of particles. This is well known. And from it, you have a Cherenkov shower, and you put your small telescope here. And the main message is here is why this is a sensitive technique, because we have, so to say, the volume, the fiducial volume is all this part of the atmosphere, which is hundreds of kilometer cubes, okay? That's why you don't need such a big telescope. It's a collaboration. We are very few people, okay? I will talk about that later, mostly in the US, United Kingdom and Italy. We are in the design phase, and we have applied for funding at the National Science Foundation in the US for one prototype telescope, okay, to be placed in the US. And we have located a location called Frisco Peak in Utah, and I will talk about that later. This is the main reference that you can check, really, in which the instrument is pretty well defined. Okay, so that was the spoiler. We know already what we will be talking about. So what is the sensitivity? Okay, where lies the sensitivity of this instrument? So you see this plot here in which you have the thickness of the ground crossed by the tau neutrinos. And here you have the probability of emergence as tau lepton, okay? You need to have some dense material in order to have a measurable probability for the tau neutrino to convert to tau. Not only that, but also for the tau to emerge from the ground and not to be absorbed within the ground. That's why you need to skim the Earth. And as you see, the best sensitivity region is with the thickness of the Earth crust between, say, 10 and 100 kilometers here. Here you have a probability that is sizable, 10%, a little bit less. And I don't know if you can see here, but it's the range of energy in which this probability is maximum. And it's about 10 to the 10, 10 to the 9, 10 to the 11 GeV. This is what we call ultra high energy range for the neutrinos, okay? What is interesting is that, first of all, basically only the probability of conversion into tau and the fact that the tau can exit the ground, the lepton, works only for the tau neutrino. So you cannot have the same situation with the electron neutrinos and the mu neutrinos, okay? The interaction, the probability of emergence and conversion is different. And what is interesting also is that once you have the tau in the atmosphere, this is a number of decay channels, okay? I don't need to go into the details, but I want to tell you that there are a lot of them, as you see here, that produce electromagnetic products, okay? Take this one, okay? For example, gammas. Of course, these are gammas at very high energies. And when you have a gamma in the atmosphere at very high energies, you have the usual particle shower generation. So from one gamma, you have pair production. From the pair production, you have Bremsstrahlung gammas and so on. And you have for some hundreds of meters or some kilometers, you have this multiplication of the particle shower, okay, until it dies out. Okay, so the particle shower is located here, but what is interesting is that from the electrons and positrons of the shower, what you have Cherenkov emission, okay, because they are superluminal velocity in the atmosphere, and you have these lights that can now propagate far away. This is the technique of the IACTs, such as HES, MAGIC, as I was saying, or Veritas. Okay, and so you put a telescope in this shadow here and you detect this Cherenkov light, which is kind of a blue ultraviolet light. You have a flash and you have your event. Okay, now this is, I don't know if you are familiar, but this is the picture of the two MAGIC telescope. We are here in the Canary Island of La Palma. Beautiful. It's a place in which you can find many telescopes, all very close one another, and the observatory is called Roque de los Muchachos. Okay. Now these are two 17-meter diameter. Now maybe you don't appreciate, but the diameter of the telescope here is 17 meter. And these are normally, they are during the day they point down, but during the night they point at the sky and do whatever they want to do with the gamma ray astronomy. Okay. By chance, okay, there is no reason, but by chance we have with MAGIC, and I'm a member of MAGIC, we have a window of visibility toward the ocean. Okay, we have the ocean in front of us. If we put the telescope pretty much down, so we have to point them slightly below the horizon, 92 degrees, we can see a pretty large fraction of the ocean. You see here the azimuth range. Okay, we have kind of 60, 70 degrees and a window of 5, 10 degrees. That's the mountain behind us. Okay, so basically we can do gamma ray astronomy during the night. Okay, but if we point the telescope toward the horizon, we can have sensitivity for these tau neutrinos, with these Earth-skimming tau neutrinos. And in this paper that was published a few years ago by MAGIC, but mainly by Michele Doro, I want to mention that, we basically assessed all the steps toward the analysis of Cherenkov light in search for tau neutrinos, all the difficulties and the sensitivity. So what is the idea? Is that when you point the telescope in that direction, I don't know if you, if you can see it. This is the telescope. The telescope here. What you have, it's a very nice situation in which you are kind of background free. Background free means that if you don't detect anything unless it is a neutrino. And this happens because the background from, say, standard event is very, very far away. Okay, it's very, very far away. The shower, the gamma shower, and so basically you don't see the light so far away. Only the muons can come there, but you can easily discriminate. While your event, the event from the tau lepton, is very close to the telescope. Okay, so the shower is very close, and then the image is very strong. So basically, we point the telescope, we wait, and if we see an event, it is very likely a tau neutrino induced event. Okay, you see here the distance is 800 kilometers versus 50 kilometers. This is an example of the events. This is Monte Carlo. Okay, we didn't detect it. So that's a typical muon ring. So that's a background event for us, and that's a typical tau lepton 1 PV neutrino event in the telescope. You can see by eyes that it's impossible to not to discriminate them. Okay. Okay, that's great. So we did this search. This is just another way to say that we can discriminate background from our signal, so we can define a signal region in which we are looking and waiting for this rare event, which is important for the thing that I would like to say after. MAGIC is not the only one. To my knowledge, there is another instrument called Ashrae. It has an electrostatic lens, and this is in Mauna Loa Island, and is also using the Earth-skimming technique, facing now to another mountain, not to the sea, but to the Mauna Kea mountain. And there is a window here in which this is the profile of the mountain, in which if you point the telescope here, you have this right fraction of the Earth crust for the probability to be maximum. Okay, this is circular, so most of the field of view you don't need, basically, only this part is active. But that's the instrument, okay? Now, the sensitivity with this kind of instrument is not that good, okay? So look here, oops, here I cut the energy, okay? It should be, I don't know, now more than PV, anyhow, and this is the sensitivity limit. Okay, so now we have here IceCube sensitivity. This is an oil plot for diffuse neutrino. We have here model of emission from a source. And here we have UHE limits. And you see here that MAGIC with 30 hours, this is our limit, and this is an extrapolation, are pretty far away from, you know, this part here in which we expect really the signals. This is the limit with Ashrae, is a little bit more sensitive, but also perform with 1,800 hours. You just put the telescope there and wait that long for event. They didn't see one event, and that's their limit. We can do similar limits by assuming one source. So you have diffuse neutrinos, but we know that we have, especially in these times now, that we can have gamma rays associated to high energy neutrinos from specific source like blazar, for example. Now, if you assume some fluxes, you can put limits to your target. Again, we are really, really far away with MAGIC, but we proved this technique. Now, how do you improve on this? Okay, what do you need? MAGIC is a very big instrument. What do you need better? Okay, so well, in order to make your telescope about this, of course, you need the cosmic neutrino flux model. You need to model the interaction of the neutrinos in the Earth, the emergence of the tau neutrinos, and then you put a telescope there. But at the end, the system is pretty simple. And no, if you have a telescope that is in the shadow, say in the shadow here of the particle, you have this chance to detect the neutrinos. And this is the basic idea. The only thing that you need is not a big telescope, not very large. You need a telescope with a wide field of view, okay? Because as I was saying, it is the atmosphere itself that is the volume, the sensitive volume of the instrument. You just need to have a telescope that is looking at a very big fraction of the atmosphere. So instead of having a circular telescope, what we were designing is this kind of instrument. I will come back to this, of course. That is kind of a section of a sphere. Okay, it's larger than taller. It's kind of a rectangular section of a sphere. This is the structure. This is the camera. We'll get back to this to the technical performance. So the idea is now to go on top of a mountain, okay, like this one. This is the Frisco Peak, and in order to have the maximum sensitivity, you can put multiple telescopes. For example, on this peak, okay, you can really place a circle of telescope, each of 60 degrees. I'm sorry that the 3D is not perfect, but basically you can cover the full horizon, okay, with few of this instrument, and this allows to multiply what is the MAGIC telescope field of view, which is few square degrees, to really hundreds of square degrees. So you can be sensitive to shower from tau neutrinos, basically from all the directions. Okay, I hope you got the idea. How is the performance of this kind of instrument? So about the collaboration, as I was saying, it's US, and I want to say that the principal investigator is Nepomuk Otte. I hope you know him. He's working in Georgia Tech, and he's really the main driver. Is the person that did most of the job so far. We have Georgia Tech, we have the University of Utah, we have United Kingdom with the University of Durham, and few institutes in Italy, okay? University of Padova, myself and Jose Mariotti, plus University of Bari and INFN. We are really, you know, when you're working in small collaboration like this, is really fun, and you can have very flexible discussion without too much politics. And I really, if you're interested in whatever part of this, we need manpower, especially if we get funds. So I really invite you to join our team, to get in contact with us if you're interested, because it's a funny collaboration. Okay, here is the link for the email. So coming back to how many, how much, how big do we need? Okay, this is done with Monte Carlo. You need to play a little bit, and this is reported here in this important work, in this physical review. Okay. So first of all, if you check the sensitivity in function of the energy, okay, this is energy, this is flux, you see that you don't need, as I say, it's important the field of view, but you don't need a very big telescope. You are more or less at the saturation, okay, so it doesn't really change if you do a telescope that is 10 meters or 100 meters, because the size of the telescope measures the density of light, okay? So the signal is so strong that with 10 or 100 meters, it doesn't really change, okay? So you don't want to make such a big telescope. This is different for magic. For magic, we need to see very faint signal, okay? And that's why we need a very big telescope. Here we need to see strong signal, but very rare. Also, you don't need to go too much high in altitude because of this geometry of the system. So, well, 0, you don't see very well the shower, but if you go to 1 kilometer, 1.5, it's already a good altitude, which is also good to build a telescope, okay? What you need is, what is more important is to have this large field of view, okay, that observe a very wide area. And what is good is, okay, this is the region, no? This is the region, sorry, where you expect to have your events. You have a neutrino that is exiting the Earth in this band here. It's good to have a veto region from the sky to have like a calibration event. You expect to have some shower now, gamma shower from here, rarely. And again, the size of, so the width of the thickness of the field of view was optimized in the fraction of the field of view above the horizon and below the horizon. And again, you see, you don't need that big field of view, because your shower at the end is contained in one small portion of your field of view. Okay, so pretty simple. It's just a reuse of one known technique with another purpose. It's not that small, because you have a telescope with, I told you, a spherical profile, overall spherical profile. You have a focal length of 4.2 meters, okay, from here, so the distance from the mirrors to the camera. You don't need very, very precise optics, because the shower is an extended object, so you don't need to have a very precise mirrors like the optical telescopes. What you have to have is this very big field of view, 60 degrees times 5, okay? Remember, magic is 2 times 2 or 3 times 3. Okay, this is 60 times 5, which by making the number comes to a telescope that is 12 meters in this direction and 3 meters high. Also, it's much simpler than magic, because you don't need to rotate the telescope. Okay, the only thing that you may want is to elevate, but in principle, if you don't want, you can even put a telescope that is in a stable position, in the optimal position, and you don't even need to move it. This is really important for such big structure, because moving this big structure is pretty complicated. Okay, here in Padova, we made this preliminary design. The camera, okay, the camera is this part in which you must have several pixels, okay? and the pixels are silicon PM. I will get back to that. The novelty of this is that in order to have such a wide field of view, which is not usual for a telescope, in order to preserve the aberration, you need to have a curved shaped camera, okay? In order to observe the right part of the mirror. So, for example, this part of the camera will see just this part of the mirror, and this part only this part of the primary mirrors. Okay. It will be there will be no shifter there. Just everything must be remote, because we want to have many telescopes, and we don't want to spend that much time for an instrument that is really waiting for the event. Okay, so there will be not much to do, but wait for the neutrino to come. So we plan remote operation. Then we started just now the optimization of the optics, which is also a funny activity here in Padova, with this program of ray tracing, in which you can really have the best image in the field of view with such a strange geometry. Also, it's important to mention that this idea of Trinity came by the experience we had with Cherenkov telescope, and by this very interesting study from Juan Cortina in Barcelona, now in Madrid, Ruben Lopez Cotto, that was a student, PhD student in Barcelona and now in Padova, and Abelardo Moralejo, maybe you know some of these guys, which basically had the same, well, they did it first, this was 2016, of this rectangular telescope, okay, but now see the size. This is 15 meters and this is 45 meters. And this is 17 meters. So this is basically like a very huge magic telescope, or very huge Trinity. Now again with a very large field of view. But this was planned to do gamma ray astronomy. Okay, so you really look at a big fraction of the sky with gamma rays, something that cannot be done for the moment, not with CTA, not with MAGIC, not with any other instrument at 100 or 2 or 1 TV. Okay, so this is a curve of the sensitivity. For example, this is 1 TV. The sensitivity of this project called Machete in 50 hours was pretty similar to, what is MAGIC? MAGIC, the blue line, and almost an order of magnitude better than Hawk. Okay, Hawk. So really good sensitivity with this instrument. If it was built, it would have really a good observation, a very good observation of the sky. Okay, it's a very nice paper. I recommend you. Okay, now to build this instrument, you need to have mirrors. The mirrors I was telling you, you don't need to have that much precision, but these are pretty good mirrors. This is one prototype that was made for CTA that we did in Padova. Look how peculiar it is. You need to have a large mirror, so you want to have it lightweight. So you have one layer here, another layer on the back, and these separators that keep the shape. And you need this PSF of a little less than 0.3 degrees, which is very easy to reach. And in one telescope, you have either 36 1-meter square mirrors or 144 quarter meter square mirrors. Okay, I don't think I need to go in this forum in details about the techniques, but this is something that can be made in repetition, in replica techniques. The camera is pretty innovative because what you have to do to have this curved camera is to use silicon PM. Silicon PM are small but very performing photon detectors in which that you can put on a camera. They are substituting in more and more instruments the standard photomultipliers. On top of a silicon PM, you put a light guide that focuses the light there, and this allows you to really shape your focal plane or your sensitive focal plane as much as you want. CTA is extensively using silicon PM to make their cameras because they're pretty sensitive instruments. So now I was saying you need one big, if you put them in a circle, you really multiply by 6 or by 6 the effective volume of atmosphere, the effective area. We computed that in order for the instrument to be successful by projecting the sensitivity, I will get back to that. We would like to have, we think we can manage 3 arrays, okay, 3 locations in the world with 6 telescopes each, okay? And maybe South America is again a candidate, okay? So we start here with 1 telescope. If we get funds, we will build all 6 in Utah. But we know that we have pretty good observatories in the Hawaii, in the Canary Islands. It's possible in China, Tibet, possibly in Australia, or maybe South Africa. I'm not sure because of the height. And in South America, you have higher mountains, but I'm pretty sure there are some locations here maybe in which we can really find a nice place. Okay, we are not now. It's too early to really start negotiating with the sites and looking for sites. We want to have our first successful instrument there. Okay, so that was where Frisco Peak is located, and we are in negotiation with the local authorities to build it. So what are the expectations for this for the sensitivity of this instrument? So first of all, because of the wide field of view, every year we will basically see the full half of the sky. Okay. Now remember, we can detect either diffuse neutrinos, okay, of that energy, or neutrinos coming from specific sources in the sky. Okay, so let's call them point light. So we have a pretty wide sky in which we can look for our data. We expect, if you have this area, you can count more or less how many TV gamma ray bursts could appear per year, and it's about 10 per year that can serendipity happens in the field of view. Every night, instead, you can scan just how to say, a strip of the sky, but which is anyhow pretty much, extremely much than what a Cherenkov telescope can do. Okay, I was saying that in principle you can keep the telescope pointed toward the ground, but this is a perfect Cherenkov telescope. So if you want to observe one gamma ray burst, for example, not the neutrinos but the gamma rays, you can really point the telescope up and track the source, so that you have sensitivity for a peculiar event that is happening in the sky. But this is not the main goal of the instrument. Now, what about the sensitivity? Okay, so let's start with the diffuse neutrinos, and you see here that we have the energy range, okay, 10 to the 8, 10 to the 9 GeV of the primary neutrinos. You have here all flavor sensitivity. These are the IceCube detection points up to 10 to the 6 GeV. This is where you have the sensitivity from these radio telescopes, radio neutrino telescope, or UHE. And this is the extrapolation of the sensitivity, okay, of two sensitivity, okay, here. Now, Trinity, if it's completed with 18 telescopes, you see that it's pretty deep here, and it's pretty deep in a region of energy larger than IceCube. Why so deep? Why so deep? Because IceCube has 1 or 2 square kilometers of ice, okay? But Trinity has hundreds of kilometer cubes in the atmosphere, okay? That's the easy interpretation. Now, we don't know what is the flux of neutrinos above that energy, so we have to extrapolate. And we did this exercise, and this is the energy of the neutrinos So this is the extrapolation in which there is no cutoff. And here in 10 years, I think, 10 years, yeah, we will see 68 neutrinos, okay? We will be able to make a pretty nice spectrum, okay? If there is no cut, if there is the hardest cutoff that you can imagine, this one, we will get just 6, okay? With this telescope, 18 telescope that we have. Okay, so in principle, we have anyhow a sensitivity for this, for any situation. However, what we can have is, okay, this will be important anyhow, okay? So by detecting this, we will be able to fill this part here in 10 years with a pretty cheap instrument, okay? $15 if you ask what is the scale of cost of a typical neutrino experiment, is pretty much more. Okay, then we have these prospects, which are more maybe, how to say, exciting for neutrino emitters, sources that can detect, that can emit neutrinos. Like, for example, you know about this NGC 1068, which is a galaxy that is the best candidate at the moment for emission of neutrinos, because you have gamma rays produced by hadrons, and then you can expect to have neutrinos there. Okay, so these kind of sources, they can appear in our wide field of view by serendipity, or we can move the telescope and point that source, okay, increasing the chances. So I'm finishing now. The takeaway message is that thanks to just a wide field of view, okay, and this peculiar design, you can boost the technique, the Cherenkov technique, to be sensitive to the skimming tau neutrinos. Okay, so at the end, one small telescope like this, it corresponds to really many big telescopes. Okay, the sensitivity is pretty interesting here, and it bridges two regions: the region of IceCube at lower energies, and the region of the radio, the huge radio installation like GRANT, for example. You see here GRANT, which has sensitivities at higher energies, okay? And that's all. We have completed the conceptual design, and we are applied for fundings, and we hope we get funded for the first prototype to be installed in the US. And I've reached the end. Thank you very much for listening.
Thank you very much, Michele. It was a very interesting apparatus, the Trinity, and all the talk in general. So, as I said before, thank you, Michele. So, for the people that is following us in the YouTube streaming, please, you can write the questions there, and we can address them to Michele. For the people that is here, if somebody want to start with a question, so we open the question session. I don't know if there is somebody. I'm going to check the... Nicolas Bernal has a question.
Yes, thank you, Michele, for the nice talk. So a couple of slides back, you talk about the few neutrinos, and you show a plot about sensitivity was for all flavors. So I was wondering why all flavors, because I understood that you were only sensitive to tau neutrinos, right?
Yeah. Sorry, I didn't make that clear. So the situation with neutrinos, cosmic neutrinos, is the following. You have when you have a source in the sky, okay, you generally produce by standard mechanism like pion decays or these kind of things. You produce neutrinos of the three families, okay, with the following, mu, with the following ratio: 1, typically 1 to 0. So at the source, you have twice mu neutrinos, then electron, and 0 tau neutrinos. But then the neutrinos cross big part of the cosmos, and the most of the theories predict that by oscillation at the Earth, the ratio between neutrino is pretty pretty perfectly mixed, okay? So now we are sensitive only to this part here, okay? To this neutrino here, the tau neutrino, yeah, tau neutrinos. But at the end, this tau neutrino was generated by all neutrinos, okay? So even if we are sensitive to just one species, these species originally come from all flavor neutrinos. So here, by all flavors, you mean that you sum this and this contribution.
Okay, thanks.
Okay, so we have some question from YouTube. So maybe if there is somebody here in the Zoom session, hold up for a moment the question. Now we are going to address the one from YouTube. There is the first question from Claudio Alejandro Muena Toledo, that he's asking why the field of view of the detecting neutrino is a few degrees from the elevation angles. He has two questions. This is the first one. And the second one, he's asking how you can differentiate a Cherenkov photon from this ultra high energy cosmic ray, gamma rays, or tan neutrino, if there is a kind of misidentification.
Okay, so the second question is this one. Yeah, it was shown here. Okay, so you have a shower. It doesn't really matter. This is a particle shower, and this is gamma or tau, or can be a proton. Okay. Now, if you have this is the particles, so mostly electron and positrons, and then out of the particle shower you have your Cherenkov light here. Okay. Now, normally, what we do with gamma rays is that if you have your telescope here, okay, by the shape, really, these different particles, they have different shapes, okay? So you can discriminate the event gamma from proton by the shape. In this, this is not what is normally done by magic. Now, in this case, as you see, what you have left, you have, oops, sorry. You have a hadronic component, okay, here. Sorry, too much technology. How can I clean this? I cannot. Anyhow, on the left plot you see the proton event. So the normal can be a gamma, can be a proton, is very far away from the telescope. Okay. So the red part is the shower, the yellow and red part is the particle shower. The lights, the Cherenkov light get absorbed. What you just have are muons. Muons can cross very large fraction of the atmosphere. The tau lepton emerging from the tau neutrino happens very close. Okay, so that's the way you separate the image. You see, on the right you have a tau-induced shower image, and on the left you have a background event. They are pretty easy to discriminate. The first question was where was it? Why you need this part? I was saying that you have your events, they happen here. Okay, sorry, here. So this is the horizon. They happen here. But you know, the event is not kind of a dot, is a wide image, and if it's not that precise, you don't know what you can really easily discriminate the event, but you cannot very precisely determine the direction. Okay, so if you have one region here in which you can expect now events directly, not neutrinos, because this is atmosphere, you have a region in which you can kind of calibrate your instrument. You know that you have event from here, not that many, and you know the direction, you can understand where they come from. Okay, I don't know if I answered clearly.
Yeah, we can wait here in the, I mean, he can answer in the YouTube chat if he understood your answer, but I guess it was pretty clear. So we have another question from in YouTube from Victor Munoz. He's asking, it is possible that the high energy sterile neutrino could also produce the same kind of signal of tau lepton. Have you studied sensitivity for such type of BSM scenario?
I'm not an expert of sterile neutrinos, but I think the word sterile is suggesting the answer. So here, sterile neutrinos can from what I know, they are candidates of dark matter because if they are in big quantities, they can interact one another. But you need to have many of them. Here, we need to have one neutrinos, okay, doing these kind of things, having a certain probability of convert. You need a charge particle here, okay? If the neutrino crosses, you don't see it. You need the neutrino to become something charged. You need the charge particle to exit the ground at the right direction with the right energy for you to detect it, okay? So that's why I think it works only with the tau neutrinos in this technique. Maybe there are some more, now I'm kind of be imaginative. There are some studies in which you can use the solar coronas as a place in which cosmic ray particles can interact. I don't know if a sterile neutrinos, but it doesn't have a strong velocity, no? So you don't have direction. So I'm not sure. So surely not as an Earth skimming technique, and I don't know about others.
Okay, so I don't know if, people in YouTube can ask more questions. They can write them in the chat. Meanwhile, we can continue with questions from here from the audience. I don't know if the rest of the people, maybe Walter has a question. I don't know.
Oh yeah, so I had a very simple question. So looking at actually the slide that you have right now, and then I think that I saw one of your plots where the sensitivity doesn't change much if you go higher than 1 kilometer or something like that, right? So there is like a big jump in the sensitivity.
Yeah.
Right. So, but looking at the picture that you have there, so the telescope is really like on the edge of the cone of the light, right?
Yeah.
So why is that the sensitivity doesn't change much once you go 1 kilometer higher?
Look, it's this geometry here. So this is, let me try if I can explain. Okay, so this is the exit. This is the exit angle from the ground, the elevation of the shower. Okay, and then you have your Cherenkov cone here. Okay, now you are very, very far away, and this is the altitude. Sorry, forget. This is the 1,000 meter of the telescope. If you are here or here, 2,000 meter, it doesn't really matter. You are hit by, you are in the shadow, say Cherenkov shadow, okay, of the event. And the original tau has crossed the right path in the ground. Okay, so what can happen is that you have to go at 5,000 meters. That would be bad, okay? But consider the geometry, so let me do it here. If you are at 1,000 kilometer, 1,000 meter here is enough. The distance from the event, it's good not to have too dim light, okay? Clearly, if you are at 5,000 meter, okay, you could see the same geometry, but now very, very far away. And this would be too far from the extraction point, okay?
Thanks.
Okay, so are there other questions? I have one question when you were talking about the possible location for the telescope. Does it matters, for instance, the possibility to access that one part of the field of view also could see towards the sea, to the ocean, or has to be inland?
No,
There is
it's
some difference
the
or
density.
any
The
cases?
density of the ocean is not that different from the density of the rock in the first. I mean, the crust. I don't know exactly how deep. So, oops. Here, no. This is the path in the ground. I don't know exactly how deep it is, but I know that in this part here, if it's water of rock, it doesn't really matter. So it's perfect if your telescope as magic looks at the ocean or at a mountain. It doesn't really matter. Also consider that you can adjust a little bit the orientation if you know the orography very well. It's just a matter of having the right position for your telescope.
Okay, so but in that sense, the kind of the ambient humidity of the sector that you see,
Sure, exactly.
Is it important for the Cherenkov, or
exactly?
Or it's better
This
a dry place or very foggy?
Exactly. Sure, exactly. So what you need to have is that from the extraction point to your telescope, you need to have as dry atmosphere as possible. Okay. As dry as possible. Really, you don't need. Well, you cannot do it in a town. Okay. But consider that the event is not that far away, and the signal is strong. We have strong signal. So even if you have clouds, for example, high in the atmosphere, you don't care about them. Okay. You need to have not too much, probably aerosol in the ground layer. But as soon as you have, typical situation of, I don't know, there are several places in the world that can do that. But you're totally right. It doesn't need to be too polluted.
Yeah, okay, so in that sense, it kind of has to be a kind of isolated place.
Yeah, for example, Utah, you have
pointing towards without any obstruction.
You need to have, so to say, clean atmosphere from few hundred meters, maybe to 1,000 meters, is where you don't need to have aerosol there. But even if it's on the ground layer, like in the desert, you don't care because the event happens on top of that layer.
Okay, thanks. No, because I was wondering when you put the case a possible site in Hawaii, I thought maybe Hawaii is too humid, but yeah, that you have the volcanoes and you can go higher and escape, like maybe from the.
I don't know if there are so many telescopes there. I'm not sure that is humid, because in the tropical part. Oops, sorry. In the tropical part, you have this Dobster circulation that you have a clean atmosphere if you go to few hundred meters high. So I don't know, but from the fact that you have so many telescopes, I think it's a pretty nice place. I'd like to go. Actually, I'd like to visit to check it myself.
Yeah, no, because also when you show the map of the possible locations, one of the telescope was in the ocean, but also looks to me like it was kind of a Easter Island. For that reason, I thought, maybe.
I put those markers. I put those markers very, very roughly.
No. But yeah. I think a telescope in Easter Island would be also awesome. Now, anyway, so another fast question. Let's say, how is the potentiality to combine this type of observation with, I don't know, surface detector or some kind of complementarity, to have many type of observatories in the same zone. So in that sense.
So for tau neutrinos, there is no need to combine it. You don't gain anything. But you're right that if you put this instrument close to a Hawk or close to even to Grant is a series of radio antennas. If you have these, it wouldn't harm because you have more accessibility. You can put it there, but combining information, the only thing that I can think of is for a flaring event. So if you have a flare and you have a Cherenkov telescope and this instrument looking at the same event at the same time, it could be interesting, but it's hard because the Cherenkov telescope point in the sky, this points in the ground. So you have to wait for the source to be at the right location. So it will never be synchronous. So as a short summary, it doesn't really help a lot, but scientifically wise, but practically, of course, having several instruments in one site is good.
Okay, yeah, because I was thinking when they have this early detection technique, I don't know, for black hole mergers, or that they expect some neutrinos coming out from there to very high energies. Yeah, would be.
No, it doesn't matter. To be on the same side, you just need to point at the same time. But to be on the same side, it doesn't change.
Yeah.
No, this of having multiple of these throughout the world, this is interesting. Yeah. A different position, but not at the same side.
Yeah, kind of. Yeah, would be the scenario in which you can have in the same line of sight from the tau neutrino, let's say, another observatory, but in the other side of the
exactly.
Earth. Let's say that
exactly.
both point to the same
exactly.
part at the same time. Yeah.
Exactly.
Okay. Good. So, and I don't know if you can mention something about the indirect searches of the dark matter. Is it feasible? Because you show in one that the capability of Trinity with 10 years is much lower. I mean, the sensitivity is much better than the other competitors like IceCube or, yeah, I mean, of course it has to be producing tau neutrinos, but
for dark matter,
there are models for
the only thing, no, for dark matter, you are not competitive to Cherenkov telescopes, normal. But for this, I don't know if you heard about this Credo collaboration, this super shower, this interaction in the sun surroundings, then yes, this instrument can be useful because it has very strong, very wide field of view. So maybe not for dark matter directly, or maybe some fancy model, but for ultra high energy events, strange events, so fundamental physics in that part, maybe yes. But for TV dark matter, other instruments are more sensitive. Yeah.
Okay, so I don't know if there are other questions. There are some comment. One comment that Aaron Vincent, he's saying, thanks for the nice talk.
Thank you for the invitation and for listening.
And I don't know if there are other questions from the people in the audience. Otherwise, we can, I guess it's time to, we have to let Michele to continue with his activities in the university. So thank you very much, Michele.
Thank you. Thank you very much for listening.
For coming here to accepting the invitation to give a talk in the lawphysics.
Thank you.
And for all the people, you know that we are going to continue with the webinars, and you can follow us here in YouTube, maybe to subscribe to the channel to be updated with the latest news, what is happening in research in astroparticle physics, particle physics, astronomy, etc. So see you all people, and stay safe. Thank you, Michele.
Thank you.